Well, welcome. This is the fourth lecture in the radar systems course, the radar equation, and it's the first main one of technical substance about radar systems engineering. All the other, like the three lectures before, the prelude, the introduction, the review of electromagnetism, and also of signals and systems and DSP, are all to bring you to this point where we start dealing with radars and explaining what they're about. Before I start this lecture, I'd just like to give you a little bit of the philosophy and flavor of how I've put this lecture together. A lot of other people have put these kinds of lectures together. They've written many books on them. And my training, as you probably have read or seen earlier, is that in school was that of a physicist, an experimental physicist. And my career was spent in the practical aspects of radar systems. And so I don't view radar as where I'd go up to a board and draw a few block diagrams, but most of it would be equations about what it would be. As I said earlier, I expect you know the math behind it, and we've been reviewing that. And so it's with that that I want you to get a good practical understanding of, if someone said to you, you're going to be a systems engineer in dealing with a radar as a whole that's being built, or a subsystem of a radar, that you have a good solid understanding of what it really is you're doing, and not just think of all the different subsystems and componentry as little black boxes. So there's going to be a fair amount of pictures showing you what these things really look like and explaining in the big picture what they are. We're not going to go into the details of a lot of the subsystems. In some cases, we'll show you examples and we'll poke down to a certain level. Other courses, you can take a course just on at some universities on waveguides. Signal processing is a whole sub-area of electrical engineering grad school. Antennas, same thing. There are plenty of places that teach a one-year course just on antennas. I'm going to focus on those subsections of antennas and how they would be used in radar systems, and what are the things that you want to know if you're going to put together all these very varied and different systems, which are mechanical in nature, computer science in nature, computer engineering in nature, physics, applied physics in nature, Maxwell's equations, the scattering off of targets, and the electrical engineering, the digital signal processing. So this is a course which brings together an awful lot of different areas. And so we'll move on from there. The radar equation is really the glue that puts together this block diagram of a radar system. It basically is telling, it connects the target properties, the reflectivity in radar cross-section, the radar characteristics themselves, like the transmitter power, the size of the antenna, the distance between the target and the radar, the range, and the properties of the medium that will affect that performance, like the atmospheric attenuation. And here we see a bunch of different blocks. And the way we're going to teach the course is to go through these blocks sequentially, some one at a time, some two at a time. And the basic point is we've got a gentleman and a lady here that are operating a radar system, are looking at the data coming out, and they control that radar and they look at the information. The first thing that's done is we generate a waveform, we amplify it, we have a switch here which lets the microwave energy flow out to the antenna. It's focused and transmitted by the antenna. It goes through the air, the propagation medium, and it scatters off the target, which has an electrical area or radar cross-section. Some of that energy scatters back into the antenna, if it's a monostatic radar, and the transmit-receive switch is now in the receive mode, where none of the transmitter power can leak through into the receiver, and then it goes into a receiver itself. It's digitized, and then we perform signal processing functions. These are functions that are, for most radars, they're hard to do in a general purpose computer. Pulse compression and Doppler filtering. Nowadays, as Moore's law exponentially gives us more power, and many radars, the Doppler filtering can be done, and this chain moves up where a general processor can do some of it. But in some radars, many of them that are complex and have to deal with complex clutter problems, you still have to use special purpose signal processing computers and architectures to perform these functions. Then you go into detecting of the target, setting a threshold so that you'll detect the target and not noise most of the time, and we'll go into the detection of signals and noise. Then from the series of detections and range azimuths that are adjacent, we'll estimate the parameters that the radar can measure, its size, amplitude, angle, range, and then we'll put together those detections that are sequential in time to track and to collect in a bunch the different detections for which we have an excellent estimate of the location of the measured estimate of the location of the target into a track which will tell us where the target is heading. And then the radar output would go to a console for users to understand, if there are air traffic controllers, that everything's safe up there in the skies, and or the data can be recorded for later. If this was a test of some kind, you'd want to record all the data you could to find out if the test went well. So we're going to look at all these different pieces. Each one is a different lecture. Some is 2 or 3. And you're going to see, after we go through the whole system of lectures, how this all fits together. But this lecture is going to talk about the glue, the equation that binds together these different target characteristics, radar characteristics, the distance, the range, and the properties of the medium. So this is the outline. In this first lecture, I'm going to do these 3 pieces, and I hope to do these 3 pieces in the last half an hour. So first, we're going to introduce the radar equation. First, what we want to understand, and I went over this a bit before, we want to detect the target, illuminate an area with enough energy so that we can detect the target of interest, measure the range, the Doppler, the angular position of the target, track it, and this says it a little better than I did before, correlate successive target detections as coming from the same object, and refine a state vector of the target. That is, its position and velocity at a given time. And then identify, if we can, is it a threat to us, or is it in danger of colliding with another aircraft? And then hand over to another sensor. It could, if it's an air traffic controller, if need be, the data collection function, but also to a missile interceptor if it's a threat, a military threat, so that the missile can knock down the target. Okay, now let's derive the radar equation. We're going to start with a source, a microwave source that's emitting a pulse, and here we see a spherical picture of that expanding pulse of electromagnetic energy, where PT is the peak power of the transmitter. It's sending out a pulse over a short unit of time. A pulse of microwave energy that's within that pulse is oscillating up and down, the real and imaginary parts are, within that pulse width. And a distance away from the radar, R, the power density at that point is given by the peak transmitter power divided by 4 pi r squared. Because the density that starts at the center of the sphere gets weaker and weaker because it's got to cover a bigger sphere. So it drops off as 1 over r squared, pi r squared being the area of the sphere. Now then, here we have that power density from an isotropic antenna, one that's emitting equally in all directions. And as we've mentioned before, the antenna can be structured so that it has gain, radiation intensity, in one direction more than another. It's got good directionality. And here is a picture of a radar antenna, in this case a parabolic dish, where the energy is transmitted back into the parabola, and then the energy leaves in a straight line. And out in the far field of the antenna and the transmitter is where you'd be detecting it, and we can see a big bump over isotropic. And the gain is the relative radiation intensity of the antenna in a given direction, this case out to sort of the northeast, over what an isotropic uniform radiating source would be. And the transmitting gain is 4 pi times the area of the aperture divided by lambda squared. And there are inefficiencies involved we usually note with an E, a sub E, for the effective area, taking into account the losses that some of the energy will scatter off the struts and the source and things like that. But this directionality isn't perfect, and some of the energy goes backwards and sideways, and these are called the side lobes. And this is on a log scale, so it doesn't mean that a third of the energy is down here. There are decades in here, probably 4 decades in this particular visualization. So the power density from a directive antenna is just the power density times that transmit gain. Now, that's the power that's in a range R, and it hits the target. And as we said earlier, the radar cross-section, RCS or sigma, is a measure of the energy that a radar target intercepts and is scattered back towards the radar. And as we took from the previous view graph, the power of the radiated signal at the target was this, from the last view graph, times sigma, the radar cross-section. And that gives us the power, not per unit area, as in the last view graph, but the power overall. And the power density of the reflected signal at the radar is just dividing by another 1 over 4 pi r squared as that wave expands backwards. So you can see that the power density of the reflected signal falls off as 1 over r squared. The transmitted signal falls off as 1 over r squared. So there's going to be a 1 over r fourth so far, as we're on our way to develop the equation. This is just taken from the last view graph. The power density of the reflected signal at the radar is this. And the received power is the power density at the radar times the area of the receiving antenna. And that's just A sub E, the effective area of this antenna. So that's the power of the reflected signal from the target and received by the radar. Now what we want to do is compare that power to the noise. And the total noise comes in from a number of different sources. It's represented by a single noise source at the output of the antenna terminal. And the noise power is stated as Boltzmann constant times the noise bandwidth of the receiver times the total system noise temperature. And you can see a Boltzmann constant is just joules per degree Kelvin. So you just have to plug in what the temperature, and if you want this to be a power, you have to multiply it by 1 over seconds or hertz, and then you'll just have the power that's of noise coming from noise sources that's also coming in along with the reflected target. And some of those sources are solar noise, galactic noise, noise from the atmosphere, it can be from lightning, from man-made sources, nearby radars, radio stations. They may not be operating on the same frequency, but their side lobes of energy in the frequency domain may interfere with this very small radar received signal that you're trying to detect. They may also be from man-made jammers that are located on airplanes that want to desensitize the radar. So it comes from many different sources, and this is the way we characterize the noise power at the receiver. So if the signal power reflected and received by the radar is this is the average noise power, we get the signal-to-noise ratio as just the ratio of those two quantities. And the assumptions are here that we have a monostatic radar, that we're using the same antenna located in the same position to receive and to transmit the signal. L are the total system losses. I call it the humanity of the radar, and we'll go into those in detail in the last half of the lecture. And T0 is just the degrees Kelvin, the ambient degrees Kelvin. So the signal-to-noise ratio is a standard measure of the radar's ability to detect a given target at a given range from the radar. And one might state, given that the wavelength is constant and the losses are constant and a few other things, we want a radar that can give us a good, healthy 13 dB, that's a factor of 20 of signal-to-noise ratio on a 1 square meter target at a certain range, 1,000 kilometers. Okay? Now let's delve a little deeper into what the system noise temperature is, the T sub S. It boils down to that there are really 5 quantities that one has to know or measure, and they're all functions of other things. T sub A is the contribution from the antenna, and T sub R is the contribution from the RF components between the antenna and the receiver. And L sub R is the loss of the input RF components in natural units, and T sub E is the temperature of the receiver. Now those 3 components can be broken down further. The contributions from the antenna are 0.88 times the sky temperature minus 254 divided by the dissipative loss within the antenna in natural units. So that will give you the contribution from the antenna. And then the T sub R, which is the contribution from the RF components, is just the physical temperature of the RF components times it's LR minus 1, where LR is the loss of the input RF components in natural units, and T sub E is, which is the temperature of the receiver, is just the ambient noise temperature times FN, which is the noise factor of the receiver, and it's a characteristic of how much noise is generated in the receiver, minus 1. Now, all these units of temperature in degrees Kelvin, and this whole area I'm just really defining for you. We're going to spend in the receiver transmitter lecture a whole section on looking in detail how these components come about, but many of them, I'll show you in a moment, can be gotten just from graphs, and they're easy to read off graphs that are well-known physical quantities. First, the noise temperature versus frequency. The effects of galactic noise, cosmic black body temperature, radiation, and solar noise and atmospheric noise due to the troposphere, it's just here in degrees Kelvin, and it's a function of elevation angle and a function of frequency. It's been measured and well documented, and so you can just take that contribution to the system noise temperature off of this graph, or one like it in Blake's book, which is a reference which has it. Many others do. Now we're going to go and look at what I'll call the surveillance form of the radar equation. Now what we've looked at so far is the track radar equation. That is, we have an antenna that's looking at a specific location in space where we know there's a target. And we're not turning the antenna around looking for targets, searching for targets. That's when we know the location of the target and we point the antenna towards the target. That's the signal-to-noise ratio, and we're going to see if the target is in the beam width. But there's another geometry that we want to look at, and that is the search example. And that is where the radar has to scan back and forth in a volume of space, a search volume, a solid angle, looking for the target till it sees it. And there, a lot of the energy goes out into space where there's no target. And so therefore you'd expect that the signal-to-noise ratio is going to depend on the solid angle that you want to search and the scan time back and forth. And you can, if you change, we've defined these earlier, the relationship between the peak and the average power. If the average power is P sub AV, the solid angle searched is omega, and T sub S is the scan time for searching that solid angle, and A sub B is the antenna effective area, then we can transform this equation into the search radar equation. And it's a useful thing. Students taking this course in diligence should just derive this equation using these definitions. They should derive this equation from this one using these definitions. And in that equation, you notice the signal-to-noise ratio is independent of wavelength. And it depends on the product of the power aperture per unit scan time. And so it doesn't say power is more important than aperture, but it's going to turn out that aperture is a lot cheaper to generate than power in most cases. And that's the search radar equation. Okay. Now let's look at the search radar equation and what does it tell us if we rewrite it into a form where we have on the left all the different design parameters in black, and on the right all the different performance parameters, and they're in blue. We've got the solid angular coverage, which we've talked about, the range coverage, the measurement quality, the time required to scan the solid angle, and the target size. And these are the things that you have in your control when you're going to design the radar. You can pick a power that you have to build the transmitter to, the area of the antenna, what the losses are. Some of them you can do something about with design, and some of them you can't. But you can't be sloppy, because the losses go up, your quality will go down. And K, Boltzmann constants, can't do much about that. And you want to lower the overall system noise, the system temperature as much as possible. Okay, now let's look at scaling the equation, and we'll look at the search equation. Say we have the power independent of wavelength, as I said. Notice it's I've recast it, so this is the average power. It's equal to everything else. It's just pulling average power onto one side, everything else on the other. Now, here we see it's a linear function of everything except the range, where it depends on the fourth power of the range. It's a very strong function of range. And to see this, let's say the radar can perform its job at 1,000 kilometers. How could we modify it to work at double the range? Well, we could increase the average power by a factor of 16, by 12 dB. That's a hefty increase in power. Or we could increase the diameter of the antenna by a factor of 4, or the area by a factor of 16, or increase the scan time by a factor of 16, 12 dB. That means that the antenna is going to go through that space. It's going to take a lot more time to go through space. So you're not going to get as many potential detections on your target as you would. Decrease the solid angle you're looking at by 12 dB, or increase the size of the cross-section you're willing to see. If you want to see small targets, that's hard. Or any appropriate combination of the above, which gains you 12 dB. So it's going to be quite a job. And likewise, you can just pop this cross-section over here, put the power down here, and it says if you want to see a very small target, you've got to do a lot of work. Now, in the next few view graphs, I'm going to go over just what the average power is. I plotted on a log-log scale. The average power required and the equivalent antenna diameter to search 1 steradian, and that's 1/12 of a sphere. 4 pi steradian is the whole solid angle in a whole sphere, but 1/12 of it in 10 seconds for a 1 square meter target and get 15 dB of signal-to-noise ratio. The losses are 10 dB, which are reasonable order of magnitude with a temperature of 500 degrees Kelvin, that would be, of course. And we're going to look at, for a number of different radars, where they fall on this chart. And you notice I put down diagonal lines of what the detection range for these parameters would be, given the different powers and antennas. So for an airport surveillance radar, the ASR-9, this is a picture of one at Logan Airport in Boston, Massachusetts. Here's where it would fall on the chart. Okay. It's got equivalent antenna diameter in the order of a few meters. That's caused, that's small because the antenna is shaped. It's bigger than that physically, but it's shaped and there are significant antenna losses, I think 9 dB, caused to give it special characteristics, which we'll go over in the antenna lecture. And it's got about 1 kilowatt of average power and can see out to about 60 for what it wants to do, which is slightly different than these numbers, what it wants to do. And you notice you're going up and up in power and aperture as you go up in this direction. This is an airport surface detection equipment located in a radome at an airport. ASDI-3 it's called. It's the third version of the ASDI. And it looks at aircraft that are just taking off and landing and taxiing on runways to make sure that the collisions don't occur on or near the ground. And it is located down here. Much smaller power. It doesn't have to see, it's got much less range that it can see, but a fair-sized antenna it's using. And next we have, I showed you the airport surveillance radar. That whole set of hundreds of them are used, many hundreds, are used all over the United States at all the major and medium-sized airports to watch air traffic where it gets dense, where it's going to land. But in between, there are regions where mostly planes are, it's not that dense, there aren't big air traffic hubs. And air route surveillance radars, in this case the ARSR-4, and here's a picture of it without its radome, is up here, and it's got more power, bigger antenna, and it can see out the order of a couple of 100 miles. And this blue object down here, we'll look into it later, is an array of a feed array, which transmits out into this reflector and generates, when you illuminate different rows or columns of the array, different beams in different, and allows this radar to have very low side lobes. So we'll go into that more in detail later. Next we have weather radars, and these are all over the country. These completely cover the United States. If you turn on your weather channel, most of the time you're seeing the output of a NextRad WSR 88D, and that NOAA runs, and that's a quite powerful radar because it's C-band. It wants to see rain and see it very carefully and measure the characteristics of weather patterns so that we'll be able to predict that a hurricane is coming or whatever. We'll show you some nice pictures of that stuff later. And lastly, the terminal Doppler wave, the radar, which is optimized, which is right here, to see a small change. It measures the Doppler in amplitude of rain and turbulence in the area around airports, and it's placed specifically at airports that have a meteorological condition called microbursts that have caused accidents. These microbursts cause an updraft and then a downdraft of air with great speed. So when a pilot who was coming in on approach, if he didn't know that this terminal Doppler weather radar did not tell the controllers to tell him to avoid that storm cell, he'd be coming in on approach, and he'd hit a force pushing him upward, and he'd be pushed the yoke down to have the plane keep him on the glide path. But just seconds later, the other side of the microburst pushes him down even further, and planes have been just pushed right into the ground and crashed with terrible accidents. So these are used by the air traffic control people to warn them where there are severe weather turbulence and shut down a specific runway if there are microbursts around that runway. There are certain geographical areas in the country that are very prone to this kind of a condition, and they obviously were first put up. And airports and airport areas that don't have that meteorological condition don't need it, so they're not put up. This system was manufactured by Raytheon. Okay, and now for the radar equation for clutter, for rain clutter, volumetric clutter. The radar equation takes a very different form when the target you're looking at, and these weather radars, the target you're looking at is rain, is distributed pretty uniformly within a given range, azimuth, elevation cell. And if the target is a diffuse scatterer like rain, which completely fills the radar azimuth elevation cell, then the radar cross-section is just the radar cross-section per unit volume times the volume. And the volume for that kind of a cell, cylindrical cell that's growing, is just this equation. Pi divided by 4 times the range and the beam width, and then the azimuth, their elevation, and the azimuth beam width, the elevation beam width, and then in the length is in range, that delta range increment is just CT over 2, and divided by a constant 2 times logarithm to the AC of 2. And note this, we're assuming a Gaussian elevation pattern of pi squared over the azimuth and elevation beam width. So the signal-to-noise ratio, when you plug this in, has the following characteristics. And note that the signal-to-noise ratio is proportional not to it's proportional to lambda squared, and that the volume distribution of the backscatter is a function of r squared rather than the usual 1 over r to the 4th. So volume distributed targets have a slightly different radar signal-to-noise equation. Okay, next, in the next half of the lecture, we're going to go over radar losses, examples, and summarize.